Hi guys, hope all of us are doing great. My name is Ernest and this is our Ernest Sciences and Mathematics TV channel. Today we are going to look at one of the strategies of trying to do this concept of integration. And this is the concept of integration by parts. Now the example I've given on the board is going to assist us try to figure out how we can be able to find an integral of such a kind of functions that we have given for the integral of x, e, exponential x, and then dx. And this is going to involve the concept of integration by parts. Now we're going to introduce a law which is going to assist us, of course, in trying to figure out how such a kind of expressions, or rather the functions can be, the integrals can be able to be achieved. And this is going to be the integral of u dv is going to be uv minus the integral of v du. So this is a rule that is going to be applicable whenever we are going to do an integration by parts. And we are going to consider the relationship that is going to exist, especially between v and u and x, by trying to give this relationship whereby we're going to give u and v, let u and v be differentiable functions of x. And therefore, we're going to use this relationship in trying to solve this one. So as per the steps we had listed for this, the concept of substitution for substitution as one of the ways in which we can be able to do integrals, then we're going to have dv be the most part. So we're going to split this specific integral into two parts. Let's say this is part A, and this is going to be part B, just for illustration purposes. So if we try to consider this, we can consider the exponential part as one of the somehow complicated part of this expression as compared to x. Since we have stated that these are simple, we can apply the simple power rule in trying to find the integral of the first part. So the second one, we're going to consider it to be a more complicated part of that specific equation. And therefore, we're going to treat this one using the basic integration formula. And of course, I leave this u as the remaining part of it. So in an actual sense, I'm trying to give this one for the section of this specific integrand, whereby u is going to be the simpler part and dv is going to be the complicated part. So if you try to consider this, then therefore I'm going to assume that the value for x is equivalent to u, and the value for dv is going to be equivalent to the exponential e of x. And therefore I'm going to have this one as let u be represented as x, and therefore dv be represented by ex. So if we try to look at this, this rule says that we're going to have this complicated portion of the integrand being given as dv, and therefore we're going to find a derivative which is going to be a simpler function of x, which is going to be given as du over dx, which is going to be equivalent from this specific case. And in this particular case, if we have dv given as ex, then v is going to be represented as ex. Now from this specific case, we had said that if we have, we can be able to recall from the rules, some rules of derivatives, whereby we have the d of dx x equivalent to e of x. Then therefore we can be able to have the integral of this specific function ex dx given as ex plus c from the exponential rules that we had mentioned in our previous video. So in this case, I'm just going to leave this one out so that we can be able to concentrate on our example for this specific derivative. So therefore, we can be able to write our integral in terms of this specific rule. So I'm going to do away with this so that we can be able to have just an elaborate way. So I can write this integral in terms of this specific function having stated what this different parts of this function imply, whereby I'm going to have the integral of x dx being given as u, whereby in this case u is going to be represented by, as I said, x. So therefore this is going to be x. And then I said that dv is going to be represented, or v is going to be represented using ex. So therefore it's going to be ex minus the integral of v. I've said that this is v du. So in this case, if I have the integral of v, we have said that v is equivalent to ex, and then we're going to have du. Now in this case, if du dx is equivalent to 1, then that implies that du is equivalent to dx given as such. So we are going to have this one substituted for this dx given as such. So if you try to look at the second part of this specific integral, I've written that post for a recap of what we can have for this specific exponential function, the integral of exponential function. And therefore, this is going to give us an answer for x, ex minus the integral of ex plus c, which is going to be given as such. So we're going to have other, of course, variant forms or complicated forms of this specific equation. Now, I've given this specific example to act as a stepping point for us in trying to solve other complex ones, which are maybe going to involve constants and other variations for this specific exponential part of this specific integral. So in this case, this is a procedure that we normally use to find integrals of functions by integration by parts. So if I try to have a quick recap for what I've mentioned, I've said that if we are given a function of this specific nature, then we let this specific we divide this specific integral elements in two parts, whereby we are going to have the first part being represented by a simpler form of that specific integrand, and the second part is going to be represented by a rather complex form of that specific integrand. Now, if I try to choose this one, if I compare x and the exponent of x, ex, then this ex is going to be a rather complex part of it. So therefore, I'm going to let u represent the simpler part of this specific exponent, specific integral, and dv, or rather v, represent the complex part of this specific integrand. Therefore, if I try to find the value for v, then therefore I'll be given of course, this is specific expression to indicate how we can be able to find what we call, of course, the value of ex from this specific dv. So therefore, v is going to be equivalent to ex given as such, and therefore we can be able to do or rewrite our expression in terms of this specific rule, which is going to be used for integration by parts in trying to do a substitution of these specific values that we have attained, whereby this particular value, the integral of this one, is going to be given as u, which is a simpler part of this specific integrand, and then the integral, and then we are going to have v being represented by this particular value for e of x, minus the integral of v. Still, we are going to have a value for v given as such, and then du. Now, I'd say that the derivative of this specific value for u is going to be equivalent to 1. So du is equivalent to dx. So we do a substitution for that one and find this one. And then lastly, we're going to see that the integral of this specific value is going to be that specific value as retained as that, as per the rules of exponential, rules of integration. So therefore, we're going to have the answer of our integral represented as such. So I hope that this is comprehensive. And catch us in our other videos that we're going to look at the variant forms of these specific integral functions, which are going to assist us, of course, know how to do this procedure of integration by parts and these various techniques of integration. So that is it for now, guys. Kindly catch us in our other videos where we're going to look at the similar approach. And of course, engage us in the comment section and subscribe to our channel so that we can have the discussion on different topics. So that is it for now, guys. Bye. God bless.